In problem number 4, we talked about an engine whose acceleration as a function of time equal its velocity as a function of time. And hopefully by now you're familiar with the fact that this is only true if, and only if, the velocity is equal to e to the t. Because e to the t is the only function, well, I guess besides 0, but we don't want it to stay at rest forever, whose derivative is equal to itself. And that's because the derivative of e to the t is e to the t. But here we want to talk about something a little bit different in problem number 5. We want to talk about an engine whose acceleration as a function of time equals, is directly proportional to its velocity as a function of time. And in order to figure this out, what I'm going to do is I'm going to do something called guess and check. I know you've probably never heard of that method before, but we like to use that all the time in math. That was sarcasm if you didn't figure it out, because hopefully you have used guess and check before sometime in your life. So what I'm going to do is I'm going to guess what velocity as a function of time is, and then check it. So in order to guess it, even k is just a constant, so we know it's not going to affect our outcome too much. So it's probably safe to assume that our function, our velocity, is still going to be very close to e to the t. Although we know it won't be exactly e to the t, because that won't satisfy this. So what I'm going to do is I'm going to guess that velocity as a function of time is equal to e to the kt. And I think it's pretty apparent why I'm guessing this, but if maybe you want to pause the video here and ponder it for a little bit and think about why would I guess this function of all functions. But moving on, so now that we've guessed it, we want to now check it to make sure it works. So if velocity as a function of time is equal to e to the kt, we know that its acceleration as a function of time is going to be the derivative of e to the kt with respect to time. And chain rule says that in order to do this, we'll take the derivative of e to the kt, and that's saying the derivative of e to the something is e to that something. So it's going to be e to the kt times the derivative of kt, because it's the inner. Now we're doing the chain rule, so it'll be the inner function, and the derivative of kt with respect to time is just k. So it's going to be e to the kt times k. And we want this to satisfy acceleration equals k times velocity. And so if acceleration is equal to e to the kt, and velocity is equal to e to the kt, and we want acceleration equal k times velocity, so we'll say that that's equal to k, right? Because that's what we're trying to check. And k times velocity, so k times e to the kt. And since we see that these two are equal, we know that this function worked. That the one that we guessed satisfied the parameters. So now that we figured out what velocity as a function of time is, the next thing we want to figure out is what is its displacement as a function of time. So we know that acceleration is the derivative of velocity, and so it follows that velocity is the derivative of displacement. So we want to know that. So we know that the derivative of whatever the displacement is. So we don't know what it is. So it's the derivative of whatever our displacement is with respect to time equals e to the kt, because that's our velocity. So the derivative of what is equal to e to the kt, and we're gonna figure this out using the same way we did here, where we're just gonna take a guess and we're gonna then check it. So the derivative of what equals e to the kt can best be solved by thinking about the chain rule, which is what we did here. So the one I'm going to guess is I'm going to say that our displacement is equal to e to the kt divided by k. And maybe here again you want to pause it to see why would I guess this, and after we check it, it should become more apparent. But it's good to think about it before we get into that. And so in order to check it, I'm going to take the derivative and make sure that it's equal to velocity. And so by taking the derivative, I'll get the derivative of e to the kt divided by k with respect to time. And since the 1 over k is a constant, it can just pop out. And the derivative of e to the kt, we already know, is going to be e to the kt times k, because we'll be using the product rule. I'm sorry, not the product rule, the chain rule. And 1 over k and k will cancel out, and we'll be left with just e to the kt, which is what we wanted. And because we proved that the derivative of our guessed displacement function is indeed equal to our velocity function. So that pretty much proves it. Now we want to put our new car to the test. So our new car is going to be facing up against another car which starts from rest, and we'll talk about its parameters up here, and we'll say that. So the other car starts from rest. Our car starts at 1 meter per second, because if our car started at rest, it goes to show that if its velocity started at 0, its acceleration would always be equal to 0, so the car would never get anywhere. It would just stay at 0 forever. So our super engine has to start with some sort of velocity. But while the other car can start at rest, because it's going to be moving with constant acceleration, like similar to what we're used to seeing. So it starts at rest. It has an acceleration constant of 8 meters per second squared. And our track is 1,600 meters long. And so I want to solve for the time it takes this car to drive the 1,600 meters. And then I'll solve for the least value of k that will make sure that our car wins. So, solving for time, we'll use our handy equation that displacement is equal to 1/2 at squared plus v naught times time. And now we're going to plug in our values, so we'll get 1,600 equals 1/2 times 8 is 4t squared, plus 0 times anything is 0, so that's goes to 0, so that term goes away. So t squared equals 400, and t equals 20. So we know that the time it's going to take, we need to find the least value of k that will ensure that our car passes the finish line in less than 20 seconds. So in order to do that, we're just going to plug in into our displacement function right here. And so we can say that, we'll do it another color, 1,600 is going to be equal to e to the k times 20 divided by k. And now we want to solve for k. So we can get started on this and trying to solve for k, but we'll quickly see how we'll run into problems, but we'll go through the steps anyway. So we get k times 1,600 equals e to the 20k, and then taking the natural log of both sides, we get natural log of k times 1,600 equals 20k, because the natural log of e to something is just that something. But now we have a problem, because we want to solve for k, but our k is in both the natural log and outside of it. So we haven't learned a function yet that will help us solve this for an exact value of k. And in fact, there is no what's called elementary function that lets us solve for k. In order to solve for k, we have to use, if we were going to solve for an exact value of k, we would use a function that's called the product log. And don't worry about what this means. We're not going to actually use it, but if that's just one, if you're the curious type, you might want to go to Wikipedia and do a search of this, because it's a pretty cool function. It helps solve equations like this. But what we're going to do is we're just going to plug it into our calculator, and we're going to say that y1 is equal to natural log of 1,600, and y2 is equal to, that y1 is equal to natural log of x times 1,600, and y2 is equal to 20 times x, and we're just going to do, our standard second calc 5 intersect, and then we'll find the intersect. And if you do that, you get that, well, I'm rounding a little bit, you'll get that k is approximately equal to 0.3104. So it's not a very high number, but we've now proven that if we've indeed built our super engine, and it can be seen right here, that it has to be the constant of proportionality, which is k, has to be at least 0.3104 if it's going to be this car right here, which is a Ferrari or something pretty fast, because a car that can accelerate at 8 meters per second squared for a full 20 seconds is a pretty damn fast car. So hopefully that made sense, and those are all. And if you gone through all the videos, then hopefully you've done all the problems in the packet, and good job. See you next time.